Okay, so I just wanted to go over what this would look like on the graphing calculator. And like I said, when I say graphing calculator, I don't necessarily just mean this portion. I mean actually using the graphing calculator to run the test. So if you go to test, in this case, you're going to go to t-test. You're going to enter your data. Now here, this is the stats. This is if it's given to you in the problem. So this is like the mean, which is your null, your sample mean, your sample standard deviation, your sample size, and then what alternative you want to use. If you already have the data into list one, if you highlight this data portion right here, what that will do is that will pull the data from list one, and then you won't actually have to enter it individually. You're going to hit calculate, and notice how it gives you your test statistic t, your p-value, your sample mean, sample standard deviation, and your sample size. So that will run the test for you. Just make sure you always have to show the work for this test statistic t and then your probability statements with p. All right, so let's go back to the same question. We're going to calculate the test statistic and the p-value for the number of minutes played during the chosen 12 hours. So we already did the conditions. We know we can use the t-distribution. Notice here how we have all of our statistics. The sample size, degrees of freedom is really important, because that is going to show us basically what t-distribution we're using. Sample mean, sample standard deviation. Now take a look at my probability statements. I'm checking to see whether or not the probability that x bar, what's the probability that I get this sample statistic or more extreme, so this sample statistic or less than that, because the direction of alternative was we say, hey, we actually think they're playing less than 50 minutes, okay? So what's the probability of getting this test statistic or more extreme? Then we're going to actually find that test statistic. Notice how I use the sample standard deviation, and then your probability statement with your t-score, okay, or your test statistic. What's the probability that I get a test statistic this far away from the mean or more extreme? And it's 0.013. So from the calculator, what you would do, remember, it's TCDF because we're looking at the t-distribution. What's the lower bound? Negative 1,000 because we're looking less than that. Up to negative 2.5764, that's our upper bound, and then degrees of freedom is 11. All right. So let's take a look at another example. Let's put everything together. The only thing that we're missing so far basically is the conclusion. So every road has one at some point, basically a speed limit. Construction zones that have a much lower speed limit. I used to drive the Pennsylvania Turnpike all the time, and they always had construction zones. Okay, so we're going to check to see if drivers, hey, do you actually obey the lower speed limits? To actually see if the drivers obey the lower speed limits, a police officer used a radar gun to measure the speed in miles per hour of a random sample of 10 drivers in a 25 miles per hour construction zone, and here are the results. Can we conclude that the average speed of drivers in this construction zone is greater than the posted 25-mile-an-hour speed limit at the alpha equals 0.05? So see if you can take a minute using your information from section 8.2, and then instead of using z-scores, knowing that we're using t-scores, see if you can do this question. So go ahead and hit pause and then take a look at the answer once you're done. Okay, so let's put it all together. Number one, make sure you include your state. What are we doing? We want to see if the average speed is higher than 25 miles per hour at the alpha equals 0.05 level. Before I do the null and alternative, I always check the conditions first, because if a condition is violated, then I might not be running the test. We know it's a simple random sample of 10 drivers in a construction zone. We know that it's independent. There's most likely more than 250 drivers in the construction zone. And in this case, since we only have 10 drivers, we're going to use a normal probability plot since the n value is less than 15 to check to see if it's approximately normally distributed. Now notice the NPP plot is linear. You must state that. How do we know that it's approximately normal? It's because the normal probability plot is linear, therefore the sample is approximately normal. All right, so we're good to go. All right, so let's put it all together. What's our null and alternative? Our null is that the mean is equal to 25. We think that they're going faster, so we're going to say, hey, we think they're going faster. The mean is greater than 5. Notice how the mean is defined. It's the mean speed of drivers in the construction zone, and then I'm using the population mean, not the sample mean. I'm using the sample to test against this. All right, so what's the name of the test? In this case, it's a one-sample t-test for means. In the last section, we did z-test, but here we have t-test. We're using means instead of proportions. Here's your statistics. Notice the degrees of freedom, your sample mean, and your sample standard deviation. What's the probability that I get, okay, because remember, we're testing to see what's the probability that I get this statistic or more extreme. All right, so let's find the t-score for that. here's our statistic minus the null divided by the standard deviation, all right, which is remember that's the same thing as your standard error, standard deviation of the statistic, and then make sure you include the probability statement with your t-score. What's the probability that I get this test statistic this extreme or more extreme in the direction which is greater than of the alternative, 0.0068, okay? You can use the t-test on the calculator to get that answer, or use your t-CDF. Just remember, don't use calculator speak. So you can use your calculator to get all the answers, but this is the work that you'll need to show, okay, in order to get full credit. All right, so let's make the conclusion. Now, that was a pretty low p-value. The conclusion is going to be the same as proportions. We're just going to be replacing means with proportions, or replacing proportions with means. Yes, there is sufficient evidence to conclude that the average speed is more than 25 miles per hour. Now this right here is your interpretation of your p-value. If the true mean is 25, then the probability of getting a test statistic as extreme as ours is 0.0069. This is statistically significant at the alpha equals 0.01 level. Notice how you're connecting the p-value to the alpha level, and that we're rejecting the null that mu is equal to 25 miles per hour. Okay, now let's just take a minute and think back to type 1 or type 2 errors. So given your conclusion, what kind of mistake, a type 1 or a type 2 error, could you have made? Explain what this means in context. All right, so just remember what the difference between a type 1 and type 2 is. Like I said, I remember that type 2 is fail to reject the null when it's false. So I basically keep the null when it's actually false, and then I can say, okay, the type 1 is the opposite. I reject the null when it's actually true. Okay, so what kind of mistake could we have made here? Okay, so we could have made a type 1 error in this case. Why could we have made a type 1 error? Well, a type 1 error is when you're rejecting the null. Okay, we could have made a type 1 error, which means we concluded that the average speed is higher than 25 when it's not actually higher than 25. Okay, we're not saying that that's like the worst or that's what we did make, but that is the error that we could have made because we rejected the null. All right, so hopefully you guys remember the game Don't Break the Ice, okay? Remember that game where it's small plastic ice cubes, they're squeezed into like a red square frame. What we're going to do, we're going to take a look at this game and see if the cubes are the width of the cubes are what they say they should be. Because think about it, whenever you have the Don't Break the Ice game, you have, I don't know, 15 cubes or whatever, but when you go to put them in, not every cube is exactly the same size. All right, remember that when you play the game, each child takes turn tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes won't collapse. For the game to work correctly, the cubes must be big enough so they hold each other in place in the plastic frame, but not so big that they're too difficult to tap out. The machine that produces the plastic cubes is designed to make the cubes that are 29.5 millimeters wide, but the actual width varies a little. So that's like anything. You go to the store and you look at a pair of jeans in the same size, they can fit 3 different ways, okay? Because there is errors during production. So to ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes, so here's your cubes, every hour and measures their width. The Fathom output summarizes the data taken from the sample during 1 hour. Okay, so this is just telling us that this is the mean of the 50 cubes. This is your n value. I took 50 cubes. This is your standard deviation, okay, and this is your standard error. So how do you know which one to use, okay? In this case, you would say, ooh, I want to use the standard error because I know that this is the standard deviation of the statistic. I don't know the population standard deviation. Okay, so first thing we're going to do is interpret the standard deviation and the standard error. Okay, so I wanted you to see what those two mean provided by the computer output. And then we're going to say, does the data give convincing evidence that the mean width of the cubes produced in this hour is not 29.5 millimeters? And we're going to use a test of significance with alpha equals 0.05. So go ahead, try this one on your own, hit pause, and then see how you do on the next couple slides. Okay, so what's the difference basically between the standard deviation and the standard error? Remember that the standard error is the standard deviation of the sample, so it's different, okay, than the standard deviation. So the standard deviation tells us that the widths of the cubes are typically about 0.090 millimeters from the mean width of 29.4846. So that's looking at a normal curve with a population distribution. It's not a sampling distribution. So the standard deviation is not from the sampling distribution. The standard error is because we're using the sample size, we're dividing by the sample size for the sampling distribution to get the sample error. So in random samples of size 50, notice the difference, the sample mean will typically be about 0.013 millimeters from the true mean. So it's just the only thing we're adding is that in samples of size 50, because in order to get that standard error, I divided by the square root of 50. Okay, I took the standard deviation divided by the square root of 50 to get your answer. Okay, so what's exactly our test look like? So same thing we did before. State, we want to test the true mean width of plastic cubes at the alpha is 0.05. Plan, what are we going to use? One sample t-test for means if the conditions are met, because we're going to use our standard error there. And this standard deviation, this is still from the sample. It's not the population standard deviation. It's a simple random sample of 50 plastic ice cubes. There's most likely more than 500 ice cubes produced by this machine in an hour. Now, how do we know that this one's normal? Now, for this one, since 50 is greater than 30, we can apply the CLT. Make sure you state by the CLT, since 50 is greater than 30, the sample will be approximately normally distributed. All right, the do, what is our, what's our null and alternative? Our null, the true mean is equal to 29.5. Now notice the question said, we don't know if it's the same or different than 29.5. So the alternative is that mu is not equal to 29.5, because we don't know if they're producing cubes that are too big or too small. We just think they're not equal to. Where mu is the true mean width of plastic ice cubes. So my do, notice how I'm showing my statistics, the sample standard deviation, the sample size, my sample mean. Now, notice how I have two probability statements here, and I actually need to add a negative right there. Okay, so when we find that sample, what is the probability that our sample mean is this extreme, 29.4846 or higher? But since we don't know if it's above that, we could also say, okay, it could also be below it. What's the probability that x bar is less than negative 29.4846? So the positive and the negative. Let's find our test statistic. Sample mean, how far away it is from our hypothesized mean, divided by the standard error, get my test statistic t. Two probability statements. What's the probability that t is less than negative 1.21, that far away from the mean, or in the lower direction, probability that t is greater than 1.21, how far away it is from the mean or greater in that direction. Okay, once you find one of these two probabilities, they're exactly the same because of symmetry, so your probability is 0.2322. Okay. This is what it would look like if you did it on the graphing calculator. Make sure that you state the degrees of freedom here. Okay, so this should say degrees of freedom equals 49. All right, so what's the conclusion? Because the p-value of 0.2322 is greater than 0.05, we fail to reject the null. There's insufficient evidence to show that the mean width is different than 29.5. Interpretation of the p-value right here. If the true mean really were 29.5, the probability of getting a sample mean as extreme as ours is 23.22%. So that's pretty high. So it's basically like saying, that can happen pretty often. So since it can happen pretty often and it's within sort of the realm of possibility, it's not statistically significant at the alpha equals 0.05 level, and we're failing to reject the null. Okay, so the last thing we are going to take a look at in this section is the connection between two-sided tests and confidence intervals. The connection between two-sided tests and confidence intervals is even stronger for means than it is for proportions. Why? That's because both inference methods for means use the standard error in the sample mean for their calculation. So when we do a confidence interval, we use the standard error. When we use the test statistic t, we use the standard error. But remember, with proportions, one of them we use the population mean, and that was for when we're just finding our z-scores, and for confidence intervals we use the sample proportion. So we were kind of using the population and the sample, but for means we're using the sample every single time. Okay, so here's your confidence interval for your test statistic. So just remember, if we have a 95% alpha level, it corresponds to a 95% significance level. Okay, and then how will we know whether or not the confidence interval supports our